Welcome to Study Loop.
This is the answer to Chapter 13, problem number 54 from the Smith Organic Chemistry textbook. This problem is giving us a molecule and telling us that when it's reacted with sodium hydride, we get an unknown molecule, W. And the problem gives us several pieces of spectrographic information about molecule W. And we're then asked to determine the structure of W and draw the stepwise mechanism that shows how we get there. And so we're given a mass spec and an IR, and you can really start sort of from either end of this problem. So sodium hydride is really only going to be able to do one thing to this starting molecule that we've been given. And so if you know how sodium hydride will react with that molecule, it's pretty straightforward to predict this structure that I've drawn here for molecule W. And the stepwise mechanism for that, as I've drawn it here, as always, lone pairs and arrows showing movement of electrons and charges in blue and reagents in green. And so the hydride is going to snag a hydrogen from the nitrogen. The nitrogen-hydrogen bond electrons will revert to the nitrogen. The negatively charged nitrogen with a second lone pair is now a very good nucleophile. Bromine, of course, is a very good leaving group. And really, whenever we see an alkyl bromide, it's probably appropriate to think that an SN2 reaction is possible. And so that's all that happens here. The nitrogen nucleophile is going to do an SN2 onto the carbon with the bromine. The bromine will leave, and you'll get this 5-membered nitrogen-containing ring. And then to use the mass spec and IR information that we were given to confirm this structure, or again, you could start from the spectral information and attack the problem that way. So first we're told that the molecular ion peak shows at 71 in the mass spectrum. And so that's an odd number, consistent with an odd number of nitrogens. Our starting molecule has 1 nitrogen, so that's probably a good place to start. So 1 nitrogen is going to account for 14 atomic mass units. 71 minus 14 gets us to 57. The most carbons that we can have to add up to 57 without going over would be 4, which accounts for 48. And then if we fill in the remaining 9 hydrogens, it gives us a formula of C4H9N. And then looking at the IR, we only really have 2 peaks in the IR, one at about 3,300, which corresponds to a nitrogen-hydrogen bond, and one in between 2850 and 3000. And that, of course, is our CsP3 hybridized carbon, and those carbons bound to their hydrogens. And so when we look at this mass spec and IR information, it does confirm the structure that we've drawn for W. And again, you could start with this information and attack the problem that way, and then try to confirm that by seeing whether this mechanism makes sense to get to the molecule that you would get from assessing the spectra. And so that is the answer to Chapter 13, problem number 54.